We start up again. As you can see here, after 5,000 iterations, we still have a pretty big error. He's getting there, but it takes forever. So omega 1, that's a bad idea. I'll put out this source code also for you, so you can play around with it if you want. This was a previous case. Can we flip it here? No. It's just another graph. If you flip your head, you have omega here, and then the number of iterations needed to find a good solution. And here it's very crude cases, 10 by 10, 20 by 20, and so on. So an optimum omega 1.5, 1.6, 1.7 when you have a few unknowns. And Jacobi, well, he could deal with omega smaller than 1, but omega bigger than 1, he explodes, as we saw. Why should you use omega smaller than 1? Then it's not over-relaxation anymore, then it's called under-relaxation. Well, sometimes we have to do that. You have an unknown, and you want to update him using a small delta something. Then we multiply this delta, the adjustments, with an omega. Normally here we do it to speed up things, but if you have a nonlinear equation system coupled, this delta here is depending on V, W, a whole bunch of other parameters, nonlinear. Things get unstable and it blows up. Then you could use an under-relaxation parameter. Multiply him with a 0.1 or 0.01 even, just to slow things down so that this updating process goes slower. That's actually frequently used as well. Final part here, consistency, convergence, and stability. So now we have different versions of the problem. You start with a partial differential equation. And here, a large U, that's the exact solution for the analytical solution for the partial differential equation, which is in general then impossible to solve. For model problems, yes, we have them, but else in general, no, you don't know these. A small u, that is the absolutely exact solution to the algebraic equations that we have obtained from our numerical scheme. So that's the solution for the discrete equation system. The difference, we call it a discretization adder. So we would have liked to have found the big U, but we don't. We can't solve the partial differential equation. What we are aiming for then is finding the little u, the numerical version, hopefully, of the big U. And we are trying to get it. We can't get it precisely, since now we are on a computer. What we can get is an approximative value, a numerical solution of our discrete equations. So this u with a wave over, that is what we actually have. So now it's depending on how many digits do you have on your computer, because it's going to be a difference here as well. So a total error, that's actually the analytical solution minus the numerical numbers that we are dealing with. And normally you split that one into two parts. So you will have a discretization error here, sort of unavoidable, and then you have a round-off error here as well. So the total error will be both. Also, you have a strange thing with your algebraic equation system. What we are aiming for is, of course, solving the algebraic equations so that they are 0 in every point for all discrete values. And that should be possible at least fairly close. This is going to be quite small. We can control it. But if you take the analytical solution and insert it into your discrete version of the same, you don't get 0. You will get, in general, something different from 0. That is what we call a truncation error. So now we say the system will be consistent if this truncation error goes to 0 when all your deltas become smaller and smaller and smaller. And we say the system will be convergent then if these two are getting closer and closer to each other for smaller and smaller deltas. Then it's a famous theorem by Lux saying now if you have a properly posed linear initial value problem, now careful, initial value problem implicitly meaning you have time in your problem, not necessarily actually, but that you have either parabolic or hyperbolic problem. You have the possibility of marching your solution forward either in time or space. So it's not for elliptical problems. And when it's properly posed, what's that mean? Properly posed, that means you have the necessary boundary conditions to solve it that we discussed the last time, depending on elliptic, parabolic, hyperbolic. And he continues, if the corresponding version, the discrete version, your numerical scheme from the partial differential equation, if that one is consistent, then all you need to obtain a solution is stability. So there comes the stability in. But to address stability, of course, you need a marching direction, or you need the marching a solution forward in time. So this does not apply for elliptical problems. They don't have this problem with stability. They can be hard to find, as we saw. You could talk about iterative stability for elliptic problems. Like when omega was too big, he blew up. Okay, that's sort of a stability as well. But when we talk about stability here, we are talking about the numerical stability for your either parabolic or hyperbolic problem. Consistent. Let's check that one. Is it consistent? How to find whether a discrete equation system is consistent or not? Well, my Fij, what is it in the example that we just had? There I had temperature, and then I need a double derivative in both directions. So here I have Ti plus 1 j minus 2 times Tij plus 2I minus 1 j divided by delta x square, double derivative in x, and then you get the same in y direction. J plus 1, and here j minus 1 divided by delta y square, this equal to 0. That was our discrete version for the Laplace equation. How can we tell that this discrete equation is a proper representation of the Laplace equation, that we are actually solving or trying to solve the correct equation? Is it consistent? How to deal with that one? Do we have mute here? I want this blue color. Never mind. We use the Taylor series. So t at a point, say I plus 1 or minus. Take the same in one swoop here. He will then be at the point I. And then it will be plus or minus the step you are going, delta, multiplied with derivative. And then you will have plus delta square half t double derivative. And then it will be plus or minus delta power 3 over 6 t 1, 2, 3. I actually need number 4 as well. Delta power 4 over 24 t 1, 2, 3, 4. Plus and minus, and then even higher order terms. So that's the Taylor in one direction. Then you do the same, but now it's going to read t I j plus minus 1, which then of course will be identical, but I use a different color for the derivatives. So here these will now represent d dy. Here this one equals d dx. Like that. Then you take your recipe, your numerical scheme, and insert the Taylor series, not for the center point where we have the focus, but for these 4 offsets here. Insert the entire Taylor series. So you see this is going to be a little bit algebra. Of course, what you do when you have a big and nasty discretization scheme, you don't do this by hand. You fire up Maple. Maple has the command Taylor, 20. Then you have 20 terms in the Taylor series, and he can do the algebra for you. So, but here, I mean, this example is fairly simple. So yes, we can do it. So what do we get when we insert the series here? Well, here I have the sum of the 2 series in the x direction, both the positive and the negative. We need to add these 2 together. So here I will have this guy twice. But I have him already here with a minus sign, so he's going to disappear. Away with him. Here I will have plus 1 term and then minus the other one. So he's also going to fall. This one is going to survive. I will have 2 times of this guy. So it will be 2 times of my delta. That is delta x square half. And then t double derivative. He survives. This one disappears. One is plus, the other is negative. This one survives. So I have 2 times of delta x power 4 over 24 t 1, 2, 3, 4, and then even higher order terms divided by delta x squared. That is my x term, and then you will get the same sort of recipe here in the y direction, delta y square half t, but now derivative with respect to y, 1, 2, and so on. Delta y 4 over 24 t 1, 2, 3, 4, and so on. So when we rewrite this one a little bit, the 2 false here, delta x squared false. So we have it something like this. Same on this side. Delta y skips and skips. So what do we get? I have this one, t double derivative with respect to x plus, and here I have t double derivative with respect to y, and then I will have plus 1 over 12, and here I will have delta x power 2 t 1, 2, 3, 4 plus t 1, 2, 3, 4 multiplied with delta y square, and then even higher order terms if you like. So this exercise is quite okay to do, not only for checking whether your scheme is consistent, that you are actually solving the correct partial differential equation, but also to check what is the order of your numerical scheme. So you can see it here quite nicely. Here you have the original partial differential equation, nabla square of t. Of course you get it. If you don't, you're in trouble. Then you're solving the wrong equation. If that one, the original partial differential equation, doesn't appear, then you have done something terribly bad. Most schemes are going to be consistent, so it shouldn't be a problem, but we have examples of schemes that is not consistent. Furthermore, we have here confirmed second order accuracy. This is the adode. What these fourth order derivatives, how big they are going to be, I have no idea. But I know the adode here is going to be of order delta x square, delta y square. So yes, they are second order accurate. So here I can say, yes, it is consistent when you do lim and let delta x and delta y go to 0 of my discrete equation, I will get back the original equation system. So yes, it is consistent, and yes, it is second order accurate. So consistency, that is something you always should check when you are inventing new numerical schemes. And that's the way to do it. You insert the Taylor series and do some algebra. This also is the way to check whether you are dealing with finite volume code, finite element code, spectral codes. You go back here to this analysis to check it. Hence, finite difference always important. Any questions to this one? That's okay. Then we don't need this anymore. So now we have covered one version of a simple iterative scheme, how to solve an elliptical equation, how to solve the Laplace equation. What we actually needed was a Poisson equation for the pressure. We were going to solve the Sura algorithm. Before we start with the Sola algorithm, I will have a little discussion here about mesh systems. We have some choices when we discretize the space. So here now is my computational cell. I mean, in the example that we had, I used I and j for these lines. So this is line number I, this is line number j. So my unknowns, they were then located here in the corners of such a cell. That's one choice. Another one would then be to say for this cell here, I use I in the center and j in the center. So here is my unknown. That would be a different mesh system. You center your unknowns. What we are dealing with now is the Navier-Stokes. So our unknown is not going to be one scalar, it's going to be two velocities and a pressure. So here I now have u, I, j, v, I, j, and in the center pressure I, j. This would sort of be, I would say, the first guess, what you would start with. Put everything in the center, or maybe even here in the corners. You could have done that as well. Have two velocities here. No, I had ij down there, sorry, here. Uij, Vij, and then the pressure also in the same location. Then you are talking co-located mesh system. Co-located mesh or co-located grid. As a first try, I mean, it should be sort of straightforward, shouldn't it? To have everything in the same point. Yes, but people run into problems. If you look at the Navier-Stokes, say just take a couple of terms here in the x direction. You have something like this, and then you have a double derivative with respect to x. Something like that. So now we do this one in a co-located mesh system. Just look at 1D. Here is my x, here is my point I, my focus point. I want to have the velocity at this point. Okay, one velocity here, that's my u, I, which is entering here for the new and the old one, divided by delta t. Here I need a double derivative. That means I'm going to need my closest neighbors as well. I need these two, I plus 1 and I minus 1, to construct a double derivative. Then I'm going to need the pressure. Not the pressure itself, but at the pressure gradient at this point. Okay, then we're using a central difference thing, and then I'm going to need, not the velocity here, I'm going to need P I plus 1 and pressure P I minus 1. The pressure at the center point does not enter the equation. That is the problem. So doing this co-located mesh, you risk operating with two separate pressure systems. It will be in two dimensions like a checkerboard pattern. Every other point, all the white ones on the checkerboard, they will have one pressure field that can be nice and smooth. But the other positions, black or white, then will have a totally different solution. They don't talk to each other. So that was the problem they run into, that you will have some oscillating pressure solutions. So co-located mesh, seems like an obvious choice, but problems with the pressure. You got quite unphysical pressure fields out of it. More modern methods can handle it. You have to sort of cheat a little bit to use the pressure there anyhow, some way. Yes, you can do that. But in the beginning, no, they sort of gave it up, this co-located idea. What they instead did was to use something called a staggered mesh. And then they called it marker and cell, MAC, marker and cell. It was an article by Harlow and Wells in '67, I think, where they simulated or tried to simulate a two-phase flow, a free surface. And they put some passive markers inside each cell that was alive, that had fluid, and then remove the marker if it were air, if it was air inside that cell. So marker and cell. And that was sort of an okay idea, but the gold in that article was the mesh they chose. And that's why we still call it a MAC system, marker and cell. They choose for cell IJ to put the pressure in the center, Pij, but the velocity is on the midpoint of the cell surfaces. So here you have Uij and here Vij. That was the stroke of genius in that article. But still we call it a MAC mesh system. And yes, we are going to use this now in the SOLA algorithm. It can be a little inconvenient to have your unknowns located at different points. A little bit of bookkeeping, and you need to have that figure quite clear in front of you when you are now starting to discretize your equations. Also, here it would be a choice. This Uij, should it be to the left or to the right? That's just a choice. So here I have chosen it to the right. So the velocity here, that's going to be Ui minus 1. And also down here, velocity in the y direction down here, that's Vij minus 1. The mesh system here becomes or makes the discrete version of your equation system very compact. I can show you as an example. Take the divergence of the velocity field. That is du dx plus dv dy. Incompressible flow, so that one should be 0. Make a discrete version of that one. Then you look at the divergence inside one single cell. And you write it like this. X derivative, that will now be Uij minus the one to the left, Ui minus 1j divided by delta x. Plus, and then Vij on the top minus the one below, j minus 1 divided by delta y. So for the divergence, I can focus on one cell. That's okay. When you look at the Navier-Stokes, then we are going to focus on, say, for instance, the x direction, Uij, time level n plus 1, minus Uij(n) divided by delta t equals, and then you have on the other side, what do you get? Well, either way, you are still now focusing on this point. For the divergence and for the pressure, you would focusing sort of on one cell, the entire cell. But addressing the new velocity, we are now looking at this point. So finding x derivative of this guy, okay, then I'm going to need the velocity over here minus this one divided by 2 times the distance. If I want a double derivative, I'm going to need these 3. If I want a double derivative in the y direction, I'm going to need these 2 together with this one. Then I have some of these convective terms, say minus u du dx minus v du dy. This has to be discretized as well. First one is not a problem. Velocity u multiplied with the derivative. I can create one with these 2. What about that in this one? I need the velocity v at that point. I don't have it at that point. I have it up here or down here. So then I'm going to need this one and this one, using these 4 to creating an average at the point where I'm standing. So this one has to be 1/4 of the sum of these, multiplied with du dy. Du dy, that's not a problem, using these 2. So that will be the entire discretization star for the u. You are looking at this one. If you have a better color here. Looking at this point, you are needing the velocities here and also the 4 v velocities as well. But still, he doesn't spread too much out in space. So all in all, it's going to be fairly compact. Before we start looking into the source code, I want to have a look at these terms, the convective terms. We talked about weak form and strong form. Here they are written on a weak form. We have a function, a non-function, multiplied with a derivative. I don't want it like that. I want it on the form derivative, only derivative. So I want to have it on the form d dx of u squared, and I want it d dy of u times v. That's how I want my convective terms. How can I do that? Can't be the same, can it? Well, let's try it out. If you take the derivative here, you will have 2 times u multiplied with du dx. So I take just one first, u du dx. I have one more, I know that, but never mind. Then here we take one on the outside, take v outside first, and then on the inside you will now have du dy. Now this looks fairly familiar. Now we are back with the convective terms as we normally write them in the Navier-Stokes. But I'm not finished. I still have one more of these, u du dx. And then I have the other one here, u outside, and then dv dy. I need that one as well. But there you see the trick. This one I can say is 0 because this is the same as the divergence of the velocity field. So yes, you can do this rearranging, taking your convective terms on this form and write them on the strong form, the derivative in front, but then you actually have used the continuity equation. That's the trick. And frequently, this is the way these terms are programmed. Not on all codes, but it happens. What was the algorithm for the projection method? Just repeat that before we take a break. The projection method, time split method. First step, calculate the tentative velocity field, call it U star, based on the old pressure from the previous time step. That velocity field is going to be wrong in general. It will not satisfy continuity. Divergence will be different from 0. But it's a very easy calculation, pure explicit expression for that one. Everything based on old values. Then we needed to solve our Poisson equation. The difference here between the new and the old pressure was equal to, what was it, rho over delta T, or the other way around, was it? I don't remember. And then the divergence of this tentative velocity field as a source term for the Poisson equation. That one we now solve using an iterative scheme. Solve that one, and we are going to solve it with SOR. We use an iterative method solving that elliptic equation. And then finally update the velocities. U n plus 1 based on the solution here. The P plus 1 pressure field, and of course also the tentative velocity field that we had. Also the last point, trivial, just one sweep of the entire field, then you have updated the velocities. So the CPU is going to burn away here, solving this elliptic equation. Any questions? Successive over relaxation, SOR. So there we use the Gauss-Seidel with the omega bigger than 1. SOR. Okay, then we take a break.